So this is a very custom component, so there's no documentation available because nobody uses it outside of Motorola, and so on and so on. So that's not a very hacker-friendly device. So the generation 1 uses an Intel X-Scale. At that time, it actually was still Intel X-Scale PXA272, I think. The power management unit they use is called Motorola PCAP. I think it's the Power Control and Audio Peripheral, PCAP. It's connected over SPI, and actually it's connected over SPI to the baseband processor and to the application processor. So you have two CPUs reading and writing to the same registers in the power management unit. It's a bit scary. Some of those registers can only be read or written from one side, but not from the other side. Yeah. The baseband processor is what they call a Neptune LTE, which, as I said, is connected over USB with some weird handshake lines. Generation 3 has the custom SoC, and a lot is unknown. If you know anything, there is multiple wikis and communities and whatnot that might be very interested in your knowledge. So one of the things, or one of the kind of, what kind of people are interested in the details of smartphone hardware anyway? It's, well, in the, let's say in the free community or in the open community outside of the respective handset manufacturers, it's mostly the people who want to put Linux on their phones. And in those cases, the system ships with Windows Mobile or some other operating systems, and then the community try to replace that. There's one community called XDA developers, which is mainly focused on HTC's various touchscreen-based Windows Mobile phones. And they had, well, it's too little developers for too many devices. The product life cycles are short, and you need to do lots of reverse engineering until you get something going, so the progress is mixed. What I have started to look at recently is the E10 Glowfish device family. This entire product portfolio, you can have them with QVGA, which is 320 by 240, or full VGA, 640 by 480 pixels, Edge or UMTS or HSDPA, keyboard or no keyboard, GPS or not, Wi-Fi or not. It's entire, like, you can have well, you can choose, pick and choose. The application processor in all of these devices that you can currently buy is the same. Well, the latest one is another one, but almost all of them is this one, which is by coincidence the same one that OpenMoko also uses. So the documentation and the Linux drivers and everything is there. So what I went through is basically reverse engineering of that hardware to some extent. I do not have the schematics. I just started to dig into it. They're very similar, as I said, to OpenMoko, which makes it interesting from the kind of Linux support side. But this is not a Linux talk, this is a hardware talk. So what they use as a Wi-Fi module is a Marvell 8686, which is the same family that is also used in the One Laptop Per Child project. So there's quite a community working with these. A Surf GPS chipset. Surf is by far, I would say, the most common GPS chipset vendor. And Cambridge Silicon Radio Bluetooth chip, which is also fairly standard. There's a CPLD, a programmable hardware device for the power management and keyboard matrix scanning. That one is sort of the only really big unknown component. And there is the Ericsson GSM modem that they use, which has a documented AT command set, but which is attached over an interesting way of using SPI, I would say. In a sense that the SPI master is the modem and the slave is your application processor. But sometimes, your application processor wants to talk to the modem, so you have to issue some handshake line like, hello, I want to talk. And then you get basically pulled by the modem. It's like, oh, yeah, now you can talk. Interesting. I mean, I think this is very typical for traditional cell phone manufacturers, right? They come from this is the cell phone. Cell phone is above everything else. So the baseband side is above everything else. The baseband side, is the master. It takes control of the communication. It takes control over the power management and so on and so on. And, that CPU, the application processor, this is just, it's just for displaying applications. It's not the actual phone part. And conceptually, if you come more from an, open source embedded devices kind of background, then obviously, the application processor is the center of the system, and the GSM modem sort of is the peripheral. So this kind of perception reflects in a way how the hardware architecture looks like. There are some cameras about which I don't care. So I started this project, the status of the project, you can check that somewhere else. So the question is, how does one go about looking or understanding more of the various hardware in those systems? Well, basically you have a number of different approaches. Number one is take the actual board apart, take notes of the major components, see if you can find anything, like Google for the identifiers on top of the components, try to get the data sheets, try to put together how the device works. This is actually fun, and I think I've been doing this with every device that I bought in, I don't know, maybe the last 10 years or so. So you just take it apart and see how it looks like. Then another option, obviously, is to use if it's a Windows mobile device, the hardware reverse engineering tool called Harrod. And then there's multiple ways how you can try to find the serial console or JTAG test pads. And obviously, you can also disassemble Windows mobile drivers, which, well, according to the European Union Copyright Directive, decompilation is not allowed, but disassembling is not decompilation, so it must be allowed. So how do you go about this? Opening the case and voiding your warranty is obviously a nice thing to do. Warranty labels you can always find on eBay and somewhere else on the net. So, yeah. This is the battery removed from the device. And as you can see, there is already some kind of connector here, or test pads. It's not really a connector, but test pads. And if you see test pads that are accessible from the outside of the device, and you can be sure there is at least a serial port and or the JTAG interface of the application processor on those pads. You just need to figure out which one is which. So, taking the device apart, well, the plastics and so on sometimes is a bit difficult, but you get the feeling for it after some time. After you remove the plastics, you get something like this. It's like, well, okay, I have 3 metal blocks. Great. Well, then you have to remove the shielding covers, which in many cases, fortunately, are snap-on shielding covers. So you actually, with a small screwdriver, maybe a scalpel, you can try to lift them. If they're soldered on, then you actually have to unsolder them or cut them open with the scalpel, which is what I did on one of my Motorola phones. So this is the uncovered application processor section. So we can again see the Samsung system on a chip in the center. This one is the CPLD, which they use for various peripherals like keyboard scanning and so on. Yeah, I think that's about it in here. It's all kinds of smaller components, nothing really important. Like this is the power supply kind of stuff. This is the HSDPA modem section. So this entire section is for. And if you think, oh, well, this is an HSDPA modem, yeah, but if you try to think what that device does, it's actually a miracle. As in, this is something that can receive and transmit on 7 different frequency bands, right? You have quad-band GSM plus tri-band 3G. And it speaks, what is it, like 3 or 4 different modulation schemes on those frequencies. It has power amplifiers for different bands and so on. So it's actually quite a lot of technology in there. For those devices like the RF3000 and the Sky whatever devices, you can actually find the data sheets if you Google for them. These are mostly the RFPA, antenna switch, all kinds of things like that. This section on the lower half is the digital baseband side. This is the flash and RAM chip and the baseband processor. Yeah, well, the backside is not as interesting. You can, as I said, Google for the various component identifiers, and then you might get an idea what those are and how they might be interconnected. Obviously, JTAG is always interesting, so if you can somehow get your hands on the JTAG interface, you can access the integrated debug macro cell that exists in every ARM processor. So you can do hardware debugging, you can single step through the code, you can take full control over the system from your hardware debugger. The question is, how do you find and use them? So the traditional method is, well, you look for the suspicious test pads on the PCB. Tracing the PCB traces on mobile phones, you can forget about that. You can do this on large devices, like maybe a Wi-Fi router or even larger devices, but on a mobile phone, no way. Typically 8-layer PCBs with very fine pitch, there's no way how you can, with your eyes, trace where the lines go. So trial and error is a good idea. Sometimes you might find schematics, which obviously then you know where they are. This is a Motorola E680 with the JTAG ports of both the application processor and, as well, interestingly, the baseband processor connected. Well, yeah, just connect to the pads and try the different signals and combinations and see what happens. And luckily, there is now a sort of a more efficient method, because JTAG is a long shift register, and you have input, out, and clock, and you can try to shift data in somewhere and see whether the same pattern shifts out somewhere else a defined number of clock cycles later. So there is a JTAG Finder project in hardware called JTAG Finder, which Hunz from the CCC, I'm sure he must be hanging out somewhere here, has implemented. And basically, you connect all the pads at once. This is the debug connector of the Glowfish device, which in the battery back, which I was talking about. You connect it to a breadboard. You connect the breadboard. Well, there's a logic analyzer as well here, but that's not really necessary. You connect the breadboard to your ARM development board. No, an AVR actually in that case, and a microcontroller development board, and then you run the JTAG Finder software, which does the brute forcing, basically, trying to find the JTAG pins. And, well, interestingly, the device was able to find the JTAG chains, both for the CPLD as well as for the application processor. And as soon as you have that, as I said, you can take full control over the system. You can do anything. Run your own code, single step through the existing code, do anything. Serial console is another useful thing. I mean, anyone who's ever dealt with like OpenWRT or similar projects, it's always useful if you have the serial console to the device in question, so you can well, see what kind of debug outputs the developers left in the final shipping firmware image, and as well to see if there's any way how you can interact with the device. So Linux-based devices or Unix-based devices, I would say in general, in quotes, including like VSDs or VxWorks or whatnot. They typically have some kind of command line interface or console or whatever on the serial port. Oh, sorry for that. Yeah, the escape button is somewhat broken after I dropped this laptop. And escape exits the application. Where were we? Yeah. Yeah. So the optimized method, as I said, you can find out about that with the JTAG Finder. We found the JTAG scans, serial console. So the transmit pin of the serial console is typically very easy to find. If you have a scope, even a very, very old analog scope from the 70s or maybe even the 60s would do, because the serial port spins are so low. You just like you keep power cycling the device on and off and on and off and on and off, which usually means battery in, out, battery in, out. And every time you power cycle, you connect your scope probe to a different test pad. And at some of the test pads, you will see patterns that, well, you can calculate the speed of the signals on the serial line for any given baud rate. So you know it must be in a certain frame. And then asynchronous serial lines have a very typical pattern that you can start to see. And then it's like, oh, this is the TXT pin. And if you connect that pin to your serial port of the computer, you will already get the output of the data. The RxD pin, which is like data from your system into the device, is much harder because you can't automatically detect it. Typically, a nice guess is left or right of the other pin. If you use some kind of resistor to make sure there's no short circuit and you connect it to each of the pins and try to transmit some things, sooner or later you will find it. In most of the cases, the number of test pads or whatever are fairly limited, so maybe it's like 30 attempts and then you have it. Don't forget to add a level shifter if you're using actual RS-232 ports. They have very different voltage levels than the voltage levels used in the device. The other approach, which is not as hardware-centric, is a hardware reverse engineering tool. It's an executable program that you can run on Windows CE devices, and it has a control socket on TCP. You connect to it from a console program on your Linux box or other box. And then basically you can do things like show me all the